Our lecture today is going to introduce us to a new number called e. The title of our section is the natural base e. You should be able to evaluate with this new natural exponential and natural logarithm functions. We will again talk about what this represents as in relationship to exponential growth and decay as well. Now, you've seen this before when we were doing compound interest, and we talked about how the formula for compounding interest, A equals P times 1 plus R over N to the power of NT, was an example of an exponential equation. If you remember, we said that the exponential situation, if we say y equals A, B, to the power of x is our exponential situation. That is our equation that we've been using, but the A represents the y-intercept. It's also that p-value in our interest problem. The B is the same as that parenthesis that represents our growth or decay factor, and then x is that exponent that comes with the compoundings times the time. So if you would do this quickly with the help of your calculator, all we want to know is what would happen, the question's really asked at the bottom, if we took $1, an investment. So if we take $1, we'll be able to tell what any amount of money would be, and it earns 100% annual interest. Of course, no bank's going to give you that, but let's do pie in the sky here and say, what if? And we're going to do it over 1 year. And then the number of compoundings per year is also going to increase, again, to a situation that's not exactly true to life. But let's see what happens. Let's look for a pattern in our numbers. We know we have $1. We know it's going to grow 100% and use these different compoundings. So do quarterly, then calculate what monthly, weekly, daily, hourly. You see I forgot or didn't do by the minute, and then by the second. And let's just see what some of our numbers come out to. What happens to that dollar? So go ahead and calculate that. I'll give you a second to get a couple of them done using your calculator. We had done a couple of these the other day in one of our previous lessons. So if you would take $1, 100% interest over 1 year, and keep increasing the compoundings, which means you're getting more and more return, but it's still only on $1, then let's take a look at these dollar values. And notice I didn't even round them to dollars and cents. I made you start looking at, again, the pattern. So I said keep 5 decimal places. So look, we went from a 2.44-ish number when we did quarterly, so 4 times a year the bank would do our account, all the way down to, if we did it by the second, let's see what happens to that $1. So even if with those 3,536,000, we're seeing a pattern. Everybody started with a 2. So it doesn't look like our dollar value is going to be ever higher than a 2. And then went from 4, 6, 6, 7, 7. So it looks like it's pretty much settling in at 7. And then it went from a next digit, 4, 1, 9. It's growing. 1, 1, 1. Looks like it's settled in at a 1. And then the third digit, 1, 3, 2, 4, 8, 8. Looks like it's settled in now at an 8. And we can continue to see that, so we can start seeing some patterns. But if we just went with that number to the nearest thousandth, 2.718-ish, the more and more times we compound, we're getting to the closer the actual value of what that dollar would earn. And this was also calculated by mathematicians far and wide over the years, and they kept finding one particular number. And that number was this new topic of the lesson today, the number E. It is that number, that continuous compounding factor. It is that naturally occurring, you might want to say, E value, E number that does come about because of our compoundings here with 1 and 100% taken over time. So let's look here at some of these characteristics. We are now going to talk about natural logs. Natural logs are a little different than logs. We said common logs were of base 10. There were all types of other logs that could be of base 2, base 3, base 5, but every single log that we call a natural log will have this number E, which represents that 2.718-ish combination. Now, E is the base. It'll be raised to a power, and it will have, again, a Y value. So anything that is of base E will be considered a natural log. Again, why? Because it naturally occurs with that calculation we just did. So if e to the x equals y, and we tried to write the inverse of that, we'd be in the same situation we were the other day when we were trying to write the inverse of a base 10. We'd have e to the y equals x. We'd try to solve that for our variable y and get y by itself. We're sort of stuck at that point because we don't know what root it is, so we're trying to take the y root of a number. So log form, again, is a good choice. So if we say the log of our number x in base e, that's the same as saying the natural log of x. So the key is anything in base e will be written as ln, natural log. And you're going to say, well, that's backwards. It has a French, I believe, derivation, and that's why it's like that. La naturale. They like to put that in front of their words. So French derivation, probably because the men who actually named it had probably some French background. So definition, the natural log of m equals n if and only if e to the n power equals m. So if I go back and read this again and read it for meaning, what is the exponent on my number m if I'm in base e and we're saying it's n? So this is saying e to the n equals m. You should be able to go back and forth between exponential and logarithmic form or natural log form very easily. So here's a couple basic ones. The ln, or natural log of 1, equals 0. Now again, if you remember doing these, you want to go right to exponentiation. If that doesn't make sense anything to you, you're going to say, well, what's my base here? Well, because of the ln, you know your base is e. E to the 0 power equals 1. That's where that came from. Any number to the 0 power is 1. This happens to be the natural log. That's how we knew we were in base e. Over here, same thing. We know our base is e to the power of 1, and it equals e. Well, true statement. Any number to the first power always equals itself. So y equals e to the x is our basic equation for all exponential base e problems. And the inverse is the x equals e to the y, like I had done up top. But you get a problem when you start trying to graph that. But we will take a look at what our graph does look like. Now, before we do that, take a quick look on your grapher, because you have e in a couple different places. You want to make sure you find it. It is not the alphabetical character like the capital E. It is a small case e, and you should have it in a couple spots on your calculator. Some of them are over by the powering keys, if you can find your powering keys. And also there's one usually over by the caret division operator keys, one there. So if you hit them, if you just hit the E key, which is mine that's over by the division key, and you just put E on your screen and then you hit equals, it's going to give you that approximation of 2.718-ish, which we said E is approximately equivalent to. Okay, and all those decimals that go with it. If you use the key that's the powering key, I think it's down by your log key, You might have to hit a second factor to access it. But if we do e to the power key, and we can put any power in there, and obviously if we want just e, we'd have to put the first power. And again, hit enter. And again, it'll spit out that 2.718-ish. Okay? So with that, let's take a look real briefly at what our regular graph. So double check a couple things. Make sure your window's on the normal window, that you have a clean slate on your graphing equation, y equals screen, and we want to put y equals e to the x. And so you can enter that two ways with either one of your E keys. And so now when we do this, we should be able to get a graph, and we should also be able to see some values. And so in our table, if we just did some of the simple values, which they always say, hey, let's graph e to the first power, e to the second power. We could go backwards, say e to the 0 power, e to the -1, e to the -2, get a few of each. And so when we graph e to the first power, we should definitely be getting that 2.718-ish. Yes, we know it goes on, but that's going to be our approximation right now. And then e to the second power, we should know is 7.3891-ish. Anything to the 0 power, we know is 1. Anything to the negative first power, we know is the reciprocal of what we had up there, but since we're using decimals, we'll go ahead and divide it. So 0.36788-ish. And e to the negative second, same thing, is the reciprocal version of what we had, so divide it, and we get a 0.13534-ish. So you can still get powers of e, because e represents a number. We don't ever write the 2.718-ish because it goes on forever. There's no repeating terms. It's just another number, just like pi is. So if we had tried to graph this using this setup, if x is 1, y is 2.78-ish, and you do have to just sort of eyeball it. My grapher's off a little. And if x is 2, it's 7.3, so 2, 4, 6, 7.3. And then 0, 1, and -1, 3.6-ish, so it is positive, 0.36-ish, I should say. So at -1, it's a 0.36-ish, so very small. And at -2, it's even smaller. So we've got that curve, and if you experiment again looking at that graph, you see that same exponential curve that we saw before. It hugs that x-axis, then starts taking off as it goes up. So it has some of the same characteristics. It definitely has the same domain, the same range, asymptote of the y-axis. The y-intercept is the same as our exponential growth equations, 0, 1. So some of those characteristics are the same. We already said, what is the inverse equation? If we flip-flop x and y, we were looking at x equals e to the y. And if we do x equals e to the y, that's where we run into troubles. Troubles being, you cannot take that, you cannot undo that, and take a square root to undo that or anything like that, because this is a y-th root. And we don't know what that y-th really is. So if we were to do the inverse of that, we'd be taking all those points that we have over there and graphing them in the y-x combination. So if I did 2.7-ish, that'd be only a 1. 2.718-ish on the x would be a 1 on the y, so I'd be about in there. A 7.3-ish, so 2, 4, 6, 7.3-ish, so a little above a 7, gives me a 2 in there. A 0, 1, so it'd be a 1, 0. A 0.36-ish, which is less than half, would down be a -1. And then a 0.13, which is even less, closer to that y-axis, closer to 0, would be down at -2. So you're seeing that arc that we talked about, that smooth curve, that inverse situation, mirrors what we learned about growth and decay exactly. So nothing new there. Just remember that the exponential y equals e to the x is very similar to your other exponentials. Now, nice part also that we shared the other day is that we have some properties, power properties, and just because it's base e is not going to change anything. You're going to see those same situations. Taking it through, if I've got e to the 0 equals 1, we get our ln of 1 equals 0. If e to the n equals e to the n, the ln of e to the n equals n. I remember I called that the sort of duh property because if you read it for meaning, we're looking at what's the exponent or the exponent on the number e to the n in base e is what? It's n. It's exponent form. That exponent should be what you're talking about. Our division should have a subtraction look to it. It's a longer one, so let's put it down here. So the ln of a single division problem equals the ln of m minus the ln. So it turns from a single log, natural log, into a double subtraction. If I multiply my exponents, I should add them. Should be very similar to what we just saw. Whoops. Okay, so the natural log of the product, m times n, is equal to the natural log of m plus the natural log of n. And then the power of a power property, e to the m n, turns into, I think we can fit it right here, the ln of x to the n. You see that power where that multiplier of n is out in front. And of course, if we need to, it could go back as an exponent. So in our work, in our simplifying these equations, we're going to be using and doing the same exact stuff we did with common logs and other bases, log logs, and now we'll do them with ln. So let's do a couple here. If I said rewrite me in logarithmic form, you're looking at definitely exponential. Everything's there. So you just have to know that you're going to start, instead of log, you're going to start out ln because we know we're in base e. And I like to do the ln on a little cursive because a lot of you, if you write ln, it looks like one n. And that could be a problem, especially if we have other numbers in the equation that look a lot like that. So ln, I put a little sign on it, a little script cursive, and then the ln of our number that we're evaluating in base e. And remember, in base e, we don't have to write that subscript down there. It's understood. And then is approximately equal to, where'd my, having a little trouble here, is approximately 3. Let's have it catch up. And I think we'll be fine. So the ln of 20.1 equals, I got a 1 there, let's do it, just to do a little erase, equals that 3. So the ln of 20.1 is equal to 3, or is approximately equal to. So if I give you something in ln form, natural log form, you should be able to write it exponentially. So as soon as you see ln, what are you thinking? Base e. Good. So from here, I need my base, e, to my exponent. That's always the number sitting by itself, to the 5.58-ish, has to be approximately that 264. And if you're not sure, because we're not expecting you to know your e's times tables, you could always go back to your calculator and do your e to the x, and this time e to the x, our exponent is a 5.58-ish. So make sure you have that, and you could get our equivalency, or what is close to it, and it does come out to be about 2.65-ish, so 2.64-ish. We're doing a little rounding. Not bad. Okay? Another situation we've been using, if we say evaluate. Evaluate means there's usually something missing. And so if you read this for meaning, you're going to be better off. Don't read it as ln unless you got the whole idea of logs down and you're feeling comfortable with them. Otherwise, I say again, read it for meaning. So what's the exponent on the number e to the negative 6 if I'm in base e? And so your answer should be, what's my exponent? Should be that negative 6. And last but not least, when we talk about and introduce a new base number, that means we're also going to be able to do some other things with our compounding. So we used to have, with general compounding formula, earlier in the chapter we've been working with a equals p times 1 plus r divided by n to the power of nt. And we called that our general compounding formula. Now the problem is, if we're compounding as fast as we possibly can, which is what this E represents, when we were doing by the second, yeah, there's nanoseconds and stuff like that with technology now, but if we could say we're doing it as fast as we possibly can and turn it over, then our new base number is going to be E. And so we have that same basic equation, you'll notice, A is A, P is P. Instead of this growth factor, which stood for our growth factor of, we had AB to the X before, it stood for the B value. Now it's that single value, our continuously compounding number of E, and then to the power of NT went away and it's replaced with RT. The rate goes up there because that is going to make a difference at what the rate is that it's compounding by. But we like to call this A equals P ER to the power of RT as our continuous compounding formula. You can do that as an example with populations of humans, bacteria. You can do prognosis with that. What's the population going to be if this continues? I like to call this one PERT. Helps you remember. A equals PERT, P-E to the power of RT. And down here, NERT. They use them both in the book. They usually tend to use the A equals equation with money, and they tend to use the N sub T with populations. So where like N sub 0 could be the initial amount of the population, and then times E to the power of RT. R being the rate the population is growing by, and T being the time that it's going to be growing. So there's a few more things to add to your plate, things to memorize, things to look on, and definitely natural log is where we're at now, not just common log base 10.